Hello, I'm Joshua Freedman, Senior Analyst at Rapaport, and welcome to the latest episode of Rapaport's LinkedIn Live series, GEMTalks, in which we speak with experts from the diamond industry about important topics affecting the sector. This episode of the GEMTalks LinkedIn Live is brought to you by GIA, the Gemological Institute of America, protecting consumers and supporting the global gem and jewelry trade since 1931 through research, education, and laboratory services. Today's topic is colored diamonds. Colored diamonds are some of the most appealing stones among consumers. Due to their rarity and beauty, they can bring in peak prices of $1 million per carat or more. In 2023, despite the diamond market downturn, a fancy, vivid blue diamond sold for around $2.5 million per carat at Christie's. The same year, a fancy, vivid purplish pink diamond fetched $3.3 million per carat at Sotheby's. We're not here to discuss the economics of this, but rather the science. Why are these diamonds so rare, and how do they get their color? What are the threats posed by color treatments and lab-grown alternatives? And how does grading work for these exceptional stones? The good news is I don't have to answer those questions myself because we have two experts from the GIA to do exactly that. They are Dr. Ulrika Johansson, Senior Manager of Diamond Research at the GIA, and Dr. Sally Eaton Magaña, the GIA's Senior Manager of Diamond Identification. Dr. Johansson's research covers the defects of natural, treated, and laboratory-grown diamond materials, and she also manages the GIA's CVD lab. She joined us in November on a previous episode of GEMTalks to discuss differences between natural and lab-grown diamonds. Dr. Eaton Magaña studies natural diamond color and the identification of treatments and lab-grown diamonds. Both of them are well placed to speak about this topic. They will give a presentation first on how diamonds get their color, and later we'll take your questions. So be sure to post your questions in the event chat throughout the session, and we will aim to cover as many of them as possible. Dr. Johansson and Dr. Eaton Magaña, welcome.
Thank you very much for the introduction, Mr. Freedman. And thank you, everyone, and Rapaport for giving us the opportunity to discuss the chemistry and physical features of fancy colored diamonds. So when a lot of people think about natural diamonds, they think about colorless materials, something that's graded in the D to Z color range. However, the truth is that diamonds can be much more exciting. You can have the full rainbow of colors as shown in this selection from the Aurora Pyramid of Hope collection. So you can have everything going from reds, yellows, blues, and greens. So very, very vibrant colors. And these, as Mr. Freedman highlighted, are extremely rare in nature. Now, GIA is, in my opinion, in one of the enviable positions where we're lucky enough that the vast majority of fancy colored diamonds come through our laboratory for grading services. And this really puts us in the position where we've been able to study, even amongst the rarest colors, several hundred samples, up to thousands and thousands of samples. So they are extremely rare, but we are very lucky that we're able to see the majority of them. So in order to discuss diamond color, we need to sort of take a step back and really just look at what diamond is in itself. So diamond is just an arrangement of carbon atoms where each carbon atom is bonded to four nearest neighbor carbon atoms, as shown in the cartoon on the right. If you had just this crystal lattice, the diamond would be perfectly colorless. Diamond is known for being transparent to wavelengths from the ultraviolet all the way through the visible into the infrared. However, diamonds are not this simple. In fact, every diamond will have small atomic level irregularities that deviate from this perfect structure. And depending on the type of deviation, the type of color center, and the concentration of this, you may also have some color. So if we step back and take a look at just the diamond lattice, so here we have just a two-dimensional structure of carbon atoms shown in gray. Now, the simplest type of deviation that you could think of or color center would be the absence of a single carbon atom. That's known as a vacancy. And this is one of the features that we'll eventually show is really important for color in diamond. But you can also have vacancy clusters shown here on the bottom right. So where you can have clusters of maybe up to 50 or so, hundreds of different little vacant lattice sites. And those can also occasionally create color. And then you can have substitutions where other elements other than carbon are substituting for the carbon atoms. So in this case, we highlight boron, but you could also have nitrogen, which is one of the most common impurities in diamond. And then you can have much more complicated structures. So nitrogen pairs, you can have nitrogen vacancy centers, so combining the nitrogens and the vacancies, and other complexes such as 3 nitrogens surrounding a vacancy and 4 nitrogens surrounding a vacancy. And, there's the full zoo of these different features. And some of these are going to be absorbing in the visible, and that's going to create color. So what we have here on the left is a diamond. You can see that white light is illuminating the stone, the incident light. Now, white consists of a rainbow of different colors. As the light goes through the stone, certain wavelengths of this light, in this case, the blue and the purple colors, are going to be absorbed. And then the transmitted light is going to instead have a yellow appearance. Now, there are several different impurities and color centers that can create yellow color. So how do we as scientists separate them? We collect what's known as a spectrum, where we look at the absorption of the light as a function of the wavelength, as shown on the right. So in this case, for this diamond, this yellow diamond, we can see that there's strong absorption in the blue and the purple ranges and specific features in the squiggle of spectra. And from that, we can say, aha, this is actually the N3 defect, so the 3 nitrogens surrounding a vacancy. And this is the type of spectra that we'll be showing you today because it allows us to recognize what particular color center is producing the color in the stone. And the presence of the color center is insufficient to create the intensity necessary for color. You need to have a high concentration of it as well. And the larger the volume of the stone, also the higher the likelihood that you'll be able to recognize the color. So now we need to think about how is color evaluated for fancy colored diamonds. Well, unlike D to Z color diamonds, the value of a fancy colored diamond depends mainly on the rarity of the color, followed by the carat weight, the cut, and the clarity. Now, the color descriptions may feel a little bit like intuitive response, yet when the romance of the color becomes the business of color, it is obviously imperative that we have a consistent and systematic color method that is developed. So GIA created the standard for fancy colored diamonds when it began issuing fancy colored diamond reports in the 1950s. And there have been periodic refinements reflecting changes in the volumes and the variety of colors that have been submitted to our labs over the years. Where the most all-encompassing description is given by an article by King and his co-authors in 1994 in Gems and Gemology. So you'll be seeing a lot of the features from that article presented now. Now, color can be described by 3 main attributes. The hue, which is the appearance of, say, red, blue, green, or anything in between, which is shown by the circle here, with a range of different fancy colored diamonds surrounding it. And fancy colored diamonds are generally described by 27 different hues shown here. The other attribute is going to be the tone, which is the relative impression of lightness or darkness to the color. And then finally, the saturation, which is the strength or the weakness of the color. And the color appearance of the stone is therefore the result of a combination of these 3 different attributes. The fancy grade, so for instance, faint, very light, fancy vivid, fancy intense, all those terms combines the effect of both the tone and the saturation, sort of illustrated here on the right. And they do depend on the hue as different colors reach their highest saturations at different levels. So there is online, you can find a color diamond color reference charts, which will really show all the different variations in the hues and the tones and the saturation that are used to determine the fancy color grades. Now, the D to Z color grading scale is based on the absence of yellow color, with D being colorless and Z being a light yellow. as shown here with the D to Z color master set. The diamonds are graded table down and examined through the pavilion facets, comparing them to these master stones. But for yellow diamonds, if the saturation is stronger than a Z color grade, they fall into the fancy color grading range, and they will be graded according to the face-up appearance instead. Brown-hued diamonds are given letter grades and color descriptions for the K to Z range. Gray-hued diamonds are given color descriptions above K. And then for any of the other hues, we're going to use fancy colored grading methodologies for anything above a G equivalent color grade. And the system is based on a side-by-side visual comparison of the diamond to one or more color comparators under controlled lighting and viewing conditions. It will be seen by more than one person. We have expert color graders, and it's an art form. And they have been extensively trained to pick up all the different regions of the diamond that show the characteristic color, rocking the diamond so that they can view the angle from perpendicular to the table to slightly off. And this is because they want to exclude any of the reflections, any of the distinction, any of those little features they want to exclude and observe what the overall characteristic color is. So here on the left, we have an example of 4 different fancy color diamonds, and you can see that it highlights in shades of gray the areas that would be seen as the characteristic color. Now, the diamond is then bracketed in this color space by 2 or more color comparators, which includes colored diamonds that we have as our master sets, or potentially opaque color chips from the Munsell color system. So if you'd like to learn more about fancy color grading, please do take a look on the materials that we have at GIA's website. It's color reference charts and the 1994 article by King and his co-authors in Gems and Gemology. And with that, we're going to move on to looking at some of the fancy color diamond ranges and what it is that is causing those colors.
Thank you very much, Ulrika. With that foundation and background, we'll start delving into the individual stories for each diamond color. Each natural diamond is unique with its own story, a story that recounts how it was created and what geologic forces it has experienced during its long history. These stories can be seen in their atomic scale defects and inclusions. And we're starting off with the yellow to orange diamonds. Yellow is the most common of the fancy color diamonds, and its close relative orange is among the rarest. Next, please. Next, please. For yellow diamonds, most of these atomic scale defects involve nitrogen. So let's review the various relevant diamond types. If a diamond has no measurable nitrogen or boron in its infrared spectrum, then it's a type 2A. If a diamond has nitrogen and those atoms are isolated from each other, then it's a type 1B. With time and temperature, while residing in the earth, those nitrogen atoms will find each other. As those diamonds pair up, then the yellow diamond can decolorize. However, there is a complication to that decolorization process because as we go down that path of nitrogen atoms pairing together, we also see the formation of some other color centers along the way, such as the N3 center, which is 3 nitrogens and a vacancy, which creates yellow color, and will be discussed more on the later slides, and the H3 color center, which is 2 nitrogens and a vacancy, and that can create yellow to greenish yellow color. Ulrika, next, please. Okay. There are 4 major causes of yellow color. Just from looking at the stones, it's difficult to distinguish how those causes might be different, but all can be revealed by analyzing their visible absorption spectra. So we're going to go through each of these. The upper left is for a Cape yellow diamond. Most yellow diamonds, about 75%, have this as their cause of color, with absorption due to a series of color centers within the blue part of the visible spectrum. A distant second in order of abundance are those diamonds that have single isolated nitrogen, about 13% of diamonds submitted to GIA. In the visible spectrum, we see a gradually increasing absorption towards the blue The responsible defect absorbs in the ultraviolet, and we see the tail of that band within the visible. The next most common cause of color is the 480 nanometer band. We don't have a better term to describe this cause of color. It's one of the current mysteries for diamond scientists, and we are researching it so that we can describe it more fully. Finally, we have diamonds that are colored by high amounts of the H3 color center. If the diamond shows only H3 related absorption and not H3 related fluorescence as well, then that will create a yellow color in the stone. Ulrika, next please. As mentioned on the previous slide, most natural yellow diamonds, about 3/4 of them, get their color from cape-related defects. The major center from this series of features is caused by the 3 nitrogens in a vacancy and occurs at 415 nanometers. And that causes absorption in the blue and creating yellow color. This center also is the major cause of blue fluorescence in natural diamond to long-wave ultraviolet light for both yellow and colorless diamonds. Next, please. The color range for yellow diamonds is dependent on its cause of color. For example, diamonds colored by isolated nitrogen can have increasing amounts of brown coloration due to the effects of plastic deformation, or increased orange color due to higher concentrations of nitrogen. Many of the orange diamonds are colored by the 480 nanometer band. And then diamonds colored by H3 can have a greenish yellow color due to combination of that yellow body color and then also green fluorescence. And next, please. Here is a collection of some of the notable yellow to orange diamonds, such as the 128 carat Tiffany yellow, found in South Africa in 1877. The pumpkin is a 5.54 carat fancy vivid orange, and its gemological assessment showed it had yellow phosphorescence and was, interestingly, type 2A, making it quite unusual for diamonds of this color. Next, please.
Thank you very much, Dr. Eaton Magaña. So moving on to blue diamonds. So this is also the case where one of the major color creating components is the presence of a substitutional defect, a substitutional color center. So some other element rather than carbon. So there are 3 causes of blue color in diamond. The most common is due to boron, a diamond that in the diamond classification system would be classified as type 2B. And you can see that you can go all the way from fancy light blue to fancy deep blue. And concentrations as low as 25 parts per billion of these boron atoms within the diamond lattice can create visible blue color. For natural diamonds, usually the concentrations go up to about 1,500 parts per billion, or in other words, 1.5 parts per million of boron replacing carbon atoms. Another frequently encountered cause of blue color are hydrogen-related features. So the actual atomic structure, such as for the 480 nanometer band that Dr. Magaña just mentioned, is unknown, but it is associated with diamonds that have an elevated concentration of hydrogen features, as observed using other spectroscopic techniques, such as FTIR. The vacancy is also occasionally the cause of color, although usually those will also have a green modifier hue. So you can see that they're oftentimes green-blue, certainly for the more intense colors. And again, that's a vacancy site. So here we have the different spectral features that can occur for these different origins. So the boron, most of the absorption for boron-related features is actually in the infrared, but there's a tail that absorbs into the red range of the visible spectrum, creating that nice blue color. The hydrogen-related features are a little bit more complicated. Again, the exact structures are not known yet, but there are features at about 530 and 720, big broad bands where the relative intensities of these are going to change the potential hue of the stone. And then at the bottom, we have the GR1 or vacancy defect. So again, a single lattice site that has been emptied out, a little small atomic level void. And those stones oftentimes have a little bit of a greenish hue to them as well as a modifier. And depending on the presence or absence of the N3 defect, that is going to make it look more greenish or bluish. And then here on the right, we have just a nice little bar chart that shows that for pure blue without any modifiers, the vast majority, over 60%, are colored by the boron. Whereas if you have something that's greenish blue, for the statistics that we conducted, they were all colored by the vacancy center. And then those that are blue-gray to gray-blue have a little bit of a mix of both, of all three different origins. Now, focusing on boron, just because that is the one that is most closely associated with a pure blue color, how does it even get into the stones? So where is the boron coming from? Well, boron is known to be strongly concentrated at the Earth's surface, yet the concentration of boron in the mantle, where the diamonds are growing, is extremely low. And this was something that puzzled scientists and geologists for a very, very long number of years. Where did this blue color from the type 2B diamonds, how did they form? Well, GI studied inclusions in these rare type 2B diamonds and determined that they formed very, very deep in the earth, reaching the lower mantle, i.e. at depths greater than 660 kilometers. And this is, as a frame of reference, about 4 times deeper than where most other kinds of diamonds form. So where did this boron come from? Well, the boron present in the oceanic crust was brought down to these extreme depths by a process called subduction. And the increase in the temperature and the pressure at those depths meant that they broke down those hydrous minerals, releasing the boron so it could be part of the growth process for the diamonds that turned into these blue stones. And this is an example where GIA is at the position where we're able to study these very, very rare diamonds and get a better understanding of the way that the Earth works. Prior to this, there was very little evidence that we had boron coming in from the oceanic crust. This is how we're able to study that. And notable blue diamonds, obviously, I mean, in this case, our laboratory is mainly based in the United States. So one of the most famous blue diamonds is, of course, going to be the Hope diamond, fancy dark grayish blue diamond, weighing 45.52 carats. That's at the Smithsonian. And this diamond has had a very exciting history. It was originally found and discovered in the Golconda region of India. It eventually made its way over into the French crown jewels. There are stories of its theft during the French Revolution, where it suddenly pops up in England, recut, and then eventually through heiresses made it over to the United States. So very, very exciting history. But then there are other beautiful blue diamonds as well. Some of the most remarkable ones that have been shown recently are the Wittelsbach Graf, the De Beers blue, and the Okavango blue from Botswana. Now moving on to green diamonds. Sally.
Okay, thank you. As we will now discuss green diamonds, one of the major causes is not due exclusively to an impurity element, like many of the causes that we've discussed previously, in which an impurity element has been incorporated into the diamond, but instead by a disruption of the diamond lattice. And we'll discuss that quite a bit in the next, on the next slide. Next slide, please. There are 4 major causes of color for these green diamonds. Typically, when we think of green diamonds, we consider those created by irradiation, which creates vacancies of the diamond lattice. That is what scientists call the GR1 defect. And I'll be mentioning GR1 quite a bit. That is one of the major causes of color and can give vibrant, pure green hues. The GR1 creates absorption within the red part of the visible spectrum. And often with natural diamonds, it's flanked by that nitrogen-related absorption within the blue, which creates a transmission window in the green part of the visible spectrum. But this is not the only cause of green color. We can see from these 4 absorption spectra that the 4 causes are all very distinct. So we can determine from the absorption spectra what is the cause of color. And then we can also know more about its treatment and its history. The next most common cause of green color is at H3 color center. And we talked about this defect with yellow diamonds. And what we see here with the green diamonds is that we have not just absorption within the blue from this H3 center, but we also have green fluorescence that contributes to this body color. The next up, we have hydrogen-related defects. As was mentioned previously, hydrogen-related defects, we know that those can create different absorption centers within the visible, but we don't fully know what is the configuration. But these hydrogen-related defects can create absorption within the red to near infrared. And when it's accompanied by nitrogen absorption in the blue, then again, that creates a transmission window within the green part of the visible spectrum. Lastly, we have nickel-related defects, which are not too common in nature, and they're actually a lot easier to produce by HPHT laboratory growth. However, if you have a natural diamond with a high amount of nickel, then that also creates an absorption feature within the red to near infrared. And again, if you have nitrogen-related absorption in the blue, then that creates a transmission window within the green. Next slide, please. So the color ranges that we see among green diamonds can vary a lot depending on that cause of color. For example, in diamonds caused by irradiation and the vacancy defect, the GR1, we can see variability in saturation due to the quantity of GR1 defects. We can also see a continuum towards blue colors, and this depends on whether the diamond has those nitrogen-related defects absorbing at blue wavelengths. If they don't, then we start to see that transmission window shift towards the blue. We can see a variation as well for the other causes of color, depending on the concentration of defects within those diamonds. And for example, for the H3, it can also depend on how strong that fluorescence is. Next slide, please. When a diamond is exposed to a laboratory or natural irradiation in the earth, this would be radioactive fluids or mineral grains, then this causes those carbon atoms to be knocked out of their home position and to reside in the spaces between their proper lattice locations. Depending on what other color centers are present in the diamond, the resulting color is green to blue. Since so many natural diamonds have nitrogen, and those CAPE-related features discussed earlier that absorb at the blue wavelengths, this is why most naturally irradiated diamonds appear as green. However, despite being exposed to irradiation, it is important to note that these diamonds are not radioactive. Next, please. Now, for the next few slides, I'll also discuss more about the radiation-related green diamonds. A lot of diamonds, while they are rough crystals, have this blue to green surface coloration, which is often called green skins. Oftentimes, this is removed by polishing. It is more difficult and more rare to receive beta or gamma radiation that will penetrate much more deeply into the stone and create a whole body coloration and turn the whole body into a green color. This typically requires radiation over a long period of geologic time, and also a very special set of conditions that allow this radiation chain reaction to move forward and to not just stop with the alpha. This unique set of conditions in nature that produce the structural imperfections in the lattice of carbon atoms across that are deeply penetrating and impact the body color are very rare. Next, please. Therefore, a green diamond's color may be confined to the surface, or in those rare cases, it can penetrate deeper into the stone. Upon preforming and faceting, the final product may be green or colorless, depending on the depth of the green coloration. Next, please. There's an additional complication as well, as preservation of the green color also requires that the radiation of that diamond to occur at very shallow depths in the earth. The reason we know that that radiation can only occur after the diamond has been brought up to the near surface region is because the green color will not survive at temperatures greater than a few hundred degrees Celsius, depending on its residence time in the earth. It also means that losing that green body color is very sensitive to polishing and to the heats generated during polishing, and so it needs to be performed by people who are well skilled in handling green color diamonds. Next, please. When describing fancy color diamonds, we use the word rare quite frequently because it so often applies, and perhaps for none more so than for the Dresden green. As mentioned earlier, the stone needs to have deeply penetrating radiation in order to create this green body color. For that to be possible in a diamond as large as the Dresden is truly astounding. For a diamond to acquire this saturated green color in nature, it must remain close to a gamma or neutron source for many, many years without being subsequently exposed to elevated temperatures. This diamond, the Dresden, was sourced from the Golconda mines in India sometime before its early historical record in 1722. And then also we show on the screen is the 5 carat Aurora Green and also the 5.51 carat Ocean Dream, which was fashioned from an 11 carat rough, which was found in Central Africa in 2002. Next, please.
Thank you. Moving on to another group of colors, so the pink to red diamonds. So unlike many of the other hue ranges that we have discussed, pink to red color diamonds have a change in the terminology. So the term pink substitutes for the term red for medium to light tones. And we can see here how you can go all the way from very light pink all the way towards the coveted fancy red color as the saturation of the red hue is increasing. Now, here we have an example of how you would find the boundary between a fancy red and, say, the fancy deep pinks or the fancy vivid pinks. So the coveted fancy red color grade is given to diamonds with a very, very limited range of tone and saturation. Hence, this is also one of the unusual color grades where there is only a single grade, fancy red. There is no such thing as a fancy deep red, for instance, or a fancy vivid red. It's just fancy red. And this is really, truly one of the most rare colors out there. We are lucky that we have been able to observe some of those in our laboratory. But again, it's a very, very limited number of stones. Only a few handfuls have been recorded in the public domain. Now, for other modifying hues, you might have pinks that have a little bit of brown or an increase in the orange hue. You can also have some that are modified by purplish colors instead, or purple. And these are all really quite closely related to each other. For the color distribution for sort of the pink group of diamonds, you can see that 40% of the ones submitted to GIA are given a pure unmodified pink hue. The next most common group being the pinkish purple or purplish pink, followed by the brownish pink to pinkish brown. And we can see here also that we have the full range of different tones as well. So you can go from faint all the way to fancy dark. And if we then look at the causes of pink color, the most common cause is an unidentified defect. So the absorption band that's associated with pink color is known as the 550 nanometer absorption band, because that is where it's absorbing. And if you have this feature plus maybe H3 centers or N3 centers or even vacancy clusters that are associated with brown color, then you're going to have the full range of modifiers that we've been observing in the last few slides. Now, Dr. Magaña has already sort of introduced the concepts behind the H3 center and the N3 center, but I'd really just like to briefly touch upon the vacancy clusters. So these vacancy clusters, along with a 550 nanometer absorption band, are features that are associated with plastic deformation. So as a diamond is deep within the earth, oftentimes in areas where there has been mountain building, you're going to have a lot of strain and stress applied to the stone. And under the temperature conditions that they're at, they might become a little bit plastic. So things shift around a little bit. And that can create vacancy clusters that can give you the brown color, in addition to the 550 nanometer absorption band defect, the pink defect, that is an unknown structure. Now, there is a second origin for pink color. This is extremely rare. It accounts for only about 0.6% of the pink color group diamonds submitted to GIA, and these are nicknamed Golconda pinks. These are generally going to be type 2 diamonds, so very, very atomically pure materials that have a high concentration of nitrogen vacancy centers, as illustrated here. And they're famous because they are associated with the historic areas of Golconda in India, although Golconda type pink diamonds exist elsewhere as well. And they also oftentimes show a very beautiful orange or red fluorescence when exposed to UV light. So they're a very, very rare group of diamonds. And here we have the absorption features that are associated with these colors. And you can see how by introducing a little bit more of the N3 center, so 3 nitrogen surrounding a vacancy, or the H3 center, the 2 nitrogen atoms surrounding a vacancy, along with a 550 band, you're going to go from a fancy pink to a fancy light purple pink, a brown pink, and even if you get rid of all of those features, you might end up with a dark brown diamond, so where you just have a plastic deformation that's creating those vacancy clusters. And then at the bottom, we have that very, very rare group of diamonds, the Golconda fancy pinks. So where they're colored instead by the absorption associated with the nitrogen vacancy centers in both the neutral and the negative charge state. And there are several notable pink and red diamonds that have been shown and have arrived in different auction houses over the last few years. Some of the biggest record holders, per carat record holders, are on this slide here, where some of them are selling for over $4 million per carat. Amongst these, I also want to highlight just a few of these. We have the Princey diamond. So this is an unusual diamond, both due to its size, but also due to the fact that the color is associated with the MV center. So this is Golconda type pink. And then on the right, I show 2 examples of fancy red, so pure unmodified fancy red diamonds, extremely rare. In particular, I'd like to highlight the Winston red diamond, a fancy red diamond weighing 2.33 carats that has recently become part of the Smithsonian collection and will be going out on an exhibit in April. So we have a new range of fancy colored diamonds with a centerpiece stone being the Winston red that is going to become yet another national treasure. And with that, I will move on to the final section of our talk that Sally will be speaking about fancy white and fancy black diamonds. Oh, sorry.
Thank you. Thank you, Dr. Janitz Johansson. Yes, we'll discuss very briefly about fancy white and fancy black diamonds. With these, instead of differences in color saturation or subtle differences in hue, instead we see differences in transparency. They can appear as translucent and progress towards opaque for both the fancy black diamonds and the fancy white. These diamonds are different from the others that we've looked at previously. Here, we are not seeing atomic scale defects, where we see a boron atom substituted in or a nitrogen atom substituted in. Instead, we're seeing color that's generally due to nanometer to micrometer sized inclusions. Another interesting difference is that fancy white diamonds can pretty much only be seen in nature. We haven't seen an example at GIA yet that has been a treated or laboratory grown fancy white diamond. Conversely, there are many ways to create treated fancy black diamonds. Next slide, please. In addition to speaking about all the causes of color for all the diamonds across the rainbow, we also wanted to show the overall distribution of natural fancy colored diamonds that have been submitted to GIA in the last 15 years. Just to clarify, these are the distributions for the primary colors. For example, the vast majority of orange diamonds have yellow or brown color modifiers. And as you can see from this pie chart, the majority of diamonds submitted have a primary color of yellow, followed by pink, brown, and green. Some hues are so rare, such as red and violet, that they have a much smaller percentage than those shown. Next, please. All right, and we're going to shift gears for this slide only and discuss laboratory-grown diamonds and their color distributions. On the left, it shows that for CVD-grown diamonds, that the dominant color among those seen at GIA is pink. Although there are at least three ways to create pink color in CVD, the majority are colored by creating nitrogen vacancy centers. Other major colors are a blue-green, that's due to laboratory radiation, a gray color due to the intentional formation of defects within the diamond, and yellow due to incorporating isolated nitrogen. On the right, for HPHT-grown diamonds, you can see that the color distribution is quite different. Almost half of the diamonds are blue-colored, often a very saturated blue color, due to boron incorporation. About 1/3 of the HPHT-grown diamonds are yellow in color due to nitrogen incorporation. And about 6% are colored green due to irradiation, or interestingly, through the combination of yellow growth sectors and blue growth sectors that combine and give a green appearance face up. Next slide. And finally, if you're interested in further reading, then we direct you to this series of articles on natural fancy colored diamonds within the Gems and Gemology journal. They have a lot of helpful information on each of the color groups. And thank you very much for your time and attention, and we hope to address any questions you might have. Thank you.
Thank you very much. That was very interesting. And just a reminder to everyone that you can post your questions in the comments, and we will, or rather in the chat, in the event chat, and we'll answer as many of them as possible. I did have a few questions of my own to begin with. You touched a little bit on color treatments. This is really for which either of you would prefer to answer. But how common are color treatments, and how hard is it to identify a diamond with treated color?
I can answer that. Certainly the commonality varies by the color. Some in which a good portion of the diamonds maybe can be susceptible to treatment, and some, like the fancy whites, we have never seen a treated color. But the vast majority of treated diamonds can be identified in a gemological laboratory. And the basic things that this gemological laboratory needs is 1, the proper instrumentation, 2, knowledgeable staff, and then also 3, an extensive database of known natural and treated samples. There certainly are some challenges, such as among those with green coloration, and we don't disclose all the features that we look for in the laboratory. But I will say that we are constantly conducting research and looking for new methods to identify, so that we can reduce the number of diamonds in which we include the color origin as undetermined.
Right, and you also touched on the issue of lab-grown colored diamonds. I had a specific question on the ease of making as-grown colored diamonds. You did touch on this in one of the slides. How common is it for colored lab-grown diamonds to be as grown, and how common is it for them to be treated after growth?
So I could maybe comment on that. For the so when it comes to fancy colored laboratory grown diamonds, in fact, the first laboratory grown diamonds that were submitted to GIA were produced by the HPHD process. And for those, it actually takes a lot of effort to get rid of color. So nitrogen, one of the primary contaminants, loves going into diamond as it's growing. For the natural diamonds, it eventually sort of decolorizes through that aggregation process, but for the laboratory grown diamonds, it stays in that isolated nitrogen state, giving yellow color. So in fact, some of the first gem quality HPHD grown products that we were observing at GIA were fancy yellow colors. Additionally, boron likes going into diamonds. So if you're able to reduce the amount of nitrogen in the system, you're able to create a type 2B blue HPHD grown diamond. For CVD diamonds, it's a little bit more complicated. There, the vast majority, if they're grown with color, it's going to be a not particularly marketable brown hue. And in fact, again, they had to work very hard to decolorize them either through treatment or grow them more pure. But it is possible to create growth conditions that can create a as grown browny pink type hue. But the vast majority of the CVD grown diamonds would be in those sort of gray, brown, or colorless ranges in their as grown states. Through treatment, on the other hand, that's when you start getting more exciting colors such as pinks. So that's a multi-treatment where they're trying to create a high concentration of nitrogen vacancy centers, both for the HPHD and the CVD laboratory grown products, or through irradiation to create that sort of greenish blue hue. Again, artificial irradiation that creates that vacancy center. So for most of the fancy color diamonds that we're seeing in the laboratory that are laboratory grown, treatment is very prevalent for the fancy colors. But again, the fancy colors are a very small proportion relative to the D to Z hued diamonds, just because of the popularity in the trade for the D to Z range of colors, well, really the colorless ranges for the laboratory grown.
Okay, great. I'm just going to move to some of the questions that came in. Let me just read this first. Does the saturation of color depend on the level of chemicals in the soil? For example, why do argyle pinks have such a deep color?
So the argyle pink diamonds are an interesting group of diamonds. They have they have a low to moderate concentration of nitrogen-related features, oftentimes highly aggregated. That in itself doesn't really create much color. However, they grow in areas. They have grown in areas that have experienced a lot of mountain building geological processes that give that the condition of plastic deformation that can create brown color. So the most common color that you would see out of the argyle mine would be brown color. But then 0.1% of their production at the time would have that 550 band feature that gives you the pink, valuable pink color. So it's not so much what's present in the soil, it's more the conditions that the diamond has experienced after growth.
Okay, another question that came in. What causes two-tone colored diamonds? Or two-color diamonds, rather.
Okay. I can take this one. It's typically due to a change in the growth process. Oftentimes, a diamond does not grow all at once. It grows and then it grows a little bit more, and it can grow at many different distinct stages. And there can be millions of years in between individual growth stages. And during that time, the surrounding chemistry can change, and then that can impact what is being incorporated into the diamond. And so there are some really beautiful examples of some two-toned examples of two-toned diamonds. And yes, they can be quite distinctive.
Okay, thank you. A couple of questions here about black diamonds. Are black diamonds found in nature, and are all natural fancy black diamonds considered type carbonado?
First, yes, there are natural black fancy black diamonds found in nature. There are several different ways in which you can create fancy black. One of the most unusual ways is if there is so much concentration of impurity elements within the stone that it creates a high amount of absorption, so that you don't need to, it's not just to a saturated color, but it's to a black color. That is very rare. Far more common, it is due to the incorporation of inclusions, and typically graphitic inclusions. And then it can also be to a contributing factor can also be due to having radiation stains on the surface that have turned brown. And so dark radiation stains combined with graphitic inclusions will often give a fancy black color. And yes, these are test as diamonds, not as carbonado.
Okay, thank you. Question here about the proportion of colored diamonds of different color. Is it possible there are more yellows than browns submitted to GIA because of the value they could sell for? I imagine it's a combination of this and their how common they are.
Yes, yeah, I would certainly think so. The statistics that we provided on that pie chart are among those diamonds that are faceted and chosen to be faceted and chosen to be submitted to GIA for color diamond grading reports. And yes, certainly that is dependent on what people choose to have those grading reports for. And that would be more common to have for the yellow diamonds than for the brown. Oftentimes, the brown diamonds we do see, they have some other modifying colors such as yellow or orange or pink that that makes it distinguish it from a straight brown color.
Okay. I had a question of my own about the master stones.
Yes.
How do you deal with master stones for colored diamonds, and how do you deal with the fact that they're so rare?
So I admit this is where I have to state that I'm not a color grader. I do
Okay.
know that the fancy color set is based on color comparators. So ideally, it's going to be diamonds. That color might have been natural, or it could have been treated to create the desirable color to have that full range of colors. But then they do also supplement it with these color chips from the Mansell color system. And that's, again, so that they can bracket and decide where in color space the stone that's being graded falls in.
What exactly are those color chips? What are they made from? Maybe I missed that.
Oh, so the color chips are pieces of card that have specific colors. So it's essentially a book full of little pieces of color, almost like paint chips. If you're choosing paint colors, you will have the full range of different paint colors. But this is a very standardized system that's internationally recognized for color description, the Mansell color system.
Do you grow master stones in the CVD lab?
No, we do not.
Okay. Thank you. Question here. Hang on. I saw a few real orange diamonds that fluoresce. Hang on. I saw a few real orange diamonds that fluoresce yellow under UVA and red under blue light. What's the reason for that? That was a submitted question.
Okay. Well, it is difficult to tell you exactly based on just hearing the description. I would want to see the spectra to know definitively what is the cause of that. Oftentimes, orange diamonds can be colored by the 480 nanometer band and will have a yellow fluorescence to shortwave UV. And then it's also nitrogen vacancy centers can fluoresce red. So there's a number of different possibilities. So it's difficult to know for sure just from hearing the description.
Okay.
Sorry.
Fair enough. Someone said their donation of a bi-colored diamond, half of the stone is chameleon, was on display this year at the Smithsonian booth at AGTA. Any thoughts on how that separation occurred?
Okay. Yeah, so we have seen a couple of those bicolored 480 band diamonds in the laboratory, and they're always interesting to see. And yeah, certainly if you look at the fluorescence imaging of a chameleon diamond, you can see that there's quite a bit of color zonation that can go on. It has a very interesting and growth history in which a lot of different events happened with the stone. Again, we don't fully know what is the cause of coloring creates the chameleon. We do know that part of the contributing factors for a chameleon is that it has a 480 nanometer band, which is in itself one of the mysteries. And then it also has some absorption up within the red infrared. And so, yeah, there's quite a bit that we are still studying about the creation of chameleons. But yeah, certainly we have seen some examples that have both a chameleon behavior in one part of the stone, and then the other part would not be a chameleon. We have seen those, yes.
Right. This is a question of mine. You've mentioned a few correlations between features of a colored diamond and their origin. Is there any, I mean, this is a topic that has been discussed on a few occasions, but is there any progress in the ability to identify the origin of a colored diamond from its physical features?
Not really. You can make a hypothesis.
Mhm.
But for some stones, particularly for, say, the nitrogen containing pinks, you can make a hypothesis, but it's really difficult to ever know for sure. Ulrika, did you have something you wanted to
Yeah.
add?
Well, so I agree that the color group that we are closest to being able to have that conversation with is the pink colored diamonds that contain nitrogen. So amongst those, they're sort of grouped into two main groups, at least the nitrogen containing ones. The ones that have very, very high concentrations of nitrogen and low aggregation states are generally associated with Russia, but they do occur in some other locations around the world as well. And then you have the others that are very high aggregation state, lower concentrations overall, and those are associated primarily with Argyle or the Namibian coast, the marine deposits off of the coast of Namibia, or even Brazil or Venezuela. But again, these type of studies require having access to diamonds from known localities and investigating using a range of different spectroscopic techniques. So because of that, it's very challenging to create these types of studies. So I'd say pinks are the ones where we're the closest, but again, they're grouped in such a way that if you had a diamond that shows features that are consistent with Russia, it doesn't mean necessarily that it's from Russia, because we have also observed diamonds with similar features that come out of areas of South Africa, for instance. So it's very difficult to separate them just based on that particular feature.
Right. Thank you for answering that. You have mentioned that obviously you're not a colored graders, or stone graders, but are you able to explain a little bit more about how the process of grading a D to Z diamond differs from the process of grading a fancy colored diamond?
So the primary difference is going to be the way that they're viewed. So in both cases, you have to work with very, very consistent lighting conditions. So we use daylight equivalent lighting in a very sort of nondescript gray background. And the samples that are D to Z, we're trying to observe the absence of color. So they're placed between and bracketed between master stones, and the viewing angle is going to be through the pavilion, just because that is how our eyes are able to perceive the absence of color more clearly. We're very sensitive to color at that angle, and we're able to minimize the effect of any of the reflections from the faceting arrangement of the stones. However, once the stone starts having a much more intense color and more saturated color in the yellow hue, that's when they will flip it over and look at the face-up appearance. If a stone has a stronger color in the face-up appearance that would push it off of the DZ color scale, then it will be graded in the face-up And again, they're going to bracket it between 2 to 3 different master stones and using them on solid color chips to see where it falls within that color space. So it's a very extensive process, and it's going to be looked at by more than one color grader, and all of the fancy colors are graded by humans, so with extensive experience.
By humans as opposed to by artificial intelligence?
As opposed to by colorimeters. So there are colorimeters that are used occasionally to supplement color grading in the D to Z color range.
I see. Thank you. Interesting question came in about colored diamonds versus colored gemstones. Are there any situations where a colored diamond could be indistinguishable from a colored gemstone of the same color with the naked eye?
The way that diamond interacts with light, its refraction and dispersion is different to that observed for fancy colored stones. So you would be able to tell the difference, say, between a red diamond versus a ruby. The way that it interacts with the light is different. So even though we have the full range of colors, so you could have the hue that is similar, the way that the stone looks is going to be distinct.
Okay. Thank you. I think we've hit the hour, so I'm very grateful, Dr. Dana Johansson and Dr. Ita Magaña, for joining us today. I've certainly learned a lot, and I hope you will have too. If anyone has any further questions, please don't hesitate to post them in the LinkedIn post for this event. A reminder, this episode of the GEMTalks LinkedIn Live is brought to you by GIA, the Gemological Institute of America, protecting consumers and supporting the global gem and jewelry trade since 1931 through research, education, and laboratory services. Thank you to everyone for participating and for sending in your questions, and have a great day or evening depending on where you are. Thank you very much.
Thank you.
Thank you.